Question 4 says, in an experiment to demonstrate the difference between alpha, beta and gamma radiation, a beam of all three radiations is directed into a uniform field. Explain why the gamma rays are undetected. So gamma is uncharged, so there can be no force on it to cause deflection. I mean, you could also point out at this stage that gamma is an electromagnetic wave, and that electromagnetic waves would not be affected by the presence of an electric field in this way. Explain why the alpha and beta particles deflect in opposite directions. So the alpha particle has a charge of +2, beta has a charge of -1, and that's relative to the electron charge. So the forces will be in opposite directions. C, explain why the beta particles are deflected more than the alpha particles. So the key idea here is it's related to their mass. So the acceleration of an object is related to the force acting on it divided by, or the resultant force acting on it divided by its mass. The force acting on these particles is related to their charge. So we have the electric field strength times the charge for the force divided by the mass. So for an individual particle, the electric field strength will be the same for all of them, so Q over M. This in physics is called the specific charge. Specific here being used as the same way as it's used in specific heat capacity, so the charge per unit mass will determine the size of the acceleration. So if we compare the two, for the alpha particle, its charge over its mass, if we just do it in relative units, it has a charge of +2 and a mass of 4 nucleons. So it has a specific charge in these units of 0.5, we'd have to say, I suppose, electron charges per nucleon. Whereas, let's do the beta particle in another colour. The beta particle has a charge of -1, sorry, charge over mass, charge of -1, and a relative mass, well, an electron is about 1/2000th the mass of a proton. So this gives us a value of -2000 electron charges per nucleon mass. So we can see the beta particle is going to be deflected much more than the alpha particle because its specific charge is so much higher. D, the deflection of a beta particle is shown in the diagram below. Let's zoom out a bit. The beta particle is travelling at a speed Vx of 0.8 c. The plates have a length of L of 0.10 meters. Find the time, that should say, that the beta particle spends in the field. So because the field is acting perpendicularly to the initial velocity Vx, then the Vx never changes. So we're just doing time is the displacement over the velocity in the horizontal direction. So the displacement is 0.10 and the velocity 0.80 times 3 times 10 to the 8. So 3 times 10 to the 8 being the speed of light, c. Let's write that up here. So 0.1 divided by 0.8 times 3 times 10 to the 8 is 4.2 times 10 to the -10 seconds. So unsurprisingly, it gets through that region incredibly quickly. The potential difference of the plates is 2,500 volts and their separation is 0.020 meters. Find the size of the acceleration. So the acceleration should be equal to the force over the mass. The force will be equal to EQ, and the electric field strength E should be V over D, so we'll end up with VQ over dm. So V, the potential difference between the plates, is 2,500. Q, the charge on the beta particle, it's an electron, so 1.6 times 10 to the minus 19. D is the separation of the plates, 0.020, and m is the mass of the beta particle, so the mass of an electron times 10 to the minus 31. Let's type that into my calculator. 2,500 times 1.6 times 10 to the minus 19 divided by 0.020 multiplied by 9.1 times 10 to the minus 31 gives me an acceleration of 2.2 times 10 to the 16 meters per second squared. So again, we can see this is very big, but we can also see from the answer above it's only going to spend a very short time accelerating in this way. So in the vertical direction, Vy is equal to Uy plus Ayt. So that's the final vertical speed is equal to the initial vertical speed. Of course, this is 0 plus the acceleration in the y direction. That's what we've worked out here. Multiplied by the time, which is what we worked out up at the top. So this will just be equal to the acceleration in the y direction, 2.2 times 10 to the minus 16, multiplied by the time it's accelerating for, 4.2 times 10 to the minus 10, times 10 to the minus 16, multiplied by 4.2 times 10 to the minus 10. Pardon me, what have I done? Sorry, that's plus 16, isn't it? That's where I've gone wrong. So that gives us an answer of 9.24 times 10 to the 6 meters per second. Find the angle of deflection theta of the beta particle. So we now know we've got our beta particle travelling with a speed in the x direction that's equal to 0.8 c, and in the y direction 9.24 times 10 to the 6 meters per second. And we want to know the size of this angle in here. So that's not a very good diagram, is it? Let's try and get that to line up. There we are. This angle in here, this is our resultant velocity obviously, so we can say theta is the inverse tan of 9.24 times 10 to the 6 over 0.8 times 3 times 10 to the 8. So let's do that. Check we're in degrees. We are. 9.24 times 10 to the 6 over 0.8 times 3 times 10 to the 8 gives us an angle of 2.2 degrees. An alpha particle travelling at this much lower speed is directed into the same region. Find its angle of deflection, theta. So we're going to need to go through the same steps. So the first step was to find the time. So the time is its speed, it's the displacement in that direction divided by the speed. So the displacement was 0.10 meters, and its speed now is 0.1 times 3 times 10 to the 8, which is 0.1 divided by, well, it's obviously just 1 over 3 times 10 to the 8, so that's 3.3 times 10 to the minus 9. Then we want to find out the acceleration. Let's use a different colour for each line here. As we had before, the acceleration is the force over the mass, but the force is the electric field strength times the charge, and the electric field strength is V over D. So we end up with VQ over dm. V was 2,500. the charge on an alpha particle is 2 lots of 1.6 times 10 to the minus 19 coulombs. The separation of the two plates, I don't remember, 0.02. And the mass of a alpha particle is 4 lots of 1.67 times 10 to the minus 19. Again, we could use 1.6 in here. It shouldn't matter too much. Everything else is to 2 significant figures. Maybe if we just use 1.7, that would have been better. So I'll write the size of the acceleration over here so I don't run out of space. 2,500 times 2 times 1.6 times 10 to the minus 19 divided by 0.020 times 4 times 1. I'm just going to use 1.7 times 10 to the minus 27. That gives me an acceleration of 5.88. So 5.9 when I write it down, times 10 to the 12 meters per second squared. I've got the acceleration and the time, so I can work out its speed in the y direction. So the vertical direction is its initial speed, but again this is 0 plus its acceleration in the y direction multiplied by the time it's in the plates for. So this is just 5.9 times 10 to the 12 multiplied by 3.3 times 10 to the minus 9. 5.9 times 10 to the 12 multiplied by 3.3 times 10 to the minus 9. So this comes out as we expect, a much smaller value, 1.9 times 10 to the 4 meters per second. So then the final step to work out its angle, I'm going to show this time it going the other way. I must admit, did it show us charges on the plates at the start? I'm not sure if it did. I'm going to show it going this way anyway. Apologies if I've got it the wrong way around. We've got our triangle now with the horizontal velocity 0.1 c, the vertical velocity 1.9 times 10 to the 4 meters per second, and we're trying to find this angle in here. Let's call it phi, because otherwise we're going to sort of have confusing symbols. So phi should equal the inverse tan of 1.9 times 10 to the 4 over 0.1 times 3 times 10 to the 8. So this is inverse tan, 1.9 times 10 to the 4 over 3.0 times 10 to the 7. Save an extra calculation, and this is 0.017 degrees. So we get to see nicely in the calculation that my beta particle, despite being much faster, is deflected by 2.2 degrees. My alpha particle only deflected by 0.017 degrees in this particular field.